Hi, welcome back. My name is Gar. I'm a third year psych student, and I recorded a video going over all of the Z procedures before in statistical inference. I went over the 1 sample and 2 sample, and I'm going to show you why that is now, because we're going to go into the T procedures, and it's going to make a lot of sense that in my mind, this is basically just a small alteration of the Z procedure. And once you know the Z procedure, the T procedure is really easy. So why do we have a T procedure instead of a Z procedure? Well, that is because in every Z procedure, we know the true population standard deviation. That is extremely unrealistic. Most of the time we don't know this. We don't know any of the true population statistics. So we kind of have to make an inference on that one as well. So instead of having the true population standard deviation, the t-test uses the sample standard deviation. So instead of the Greek letter, we now use the S. And because we are making an inference on one of our numbers, we need to have a little bit more wiggle room for mistakes. And we do that by having degrees of freedom. Degrees of freedom give us a little bit extra error room, so we will have larger numbers, but at least we are relatively sure that we're not incorrect, kind of thing. For the first samples, which are going to be 1 sample T procedures, it's going to be n minus 1. And once we have 2 samples, it is the smaller one, like the smaller sample minus 1. But we'll go over that. So that is the one difference. So every time when you are presented with a question and you are given a sample mean, you instantly know you're doing a T procedure. If you are given a population mean, that is a Z procedure. Other than that, it is the exact same. So we have our Z procedure, which was X bar minus mu divided by the standard deviation divided by the square root of n. For the T procedure, we now have X minus mu divided by S divided by n. That is the only difference. It's the only difference. Plus that we now have a degrees of freedom of n minus 1. Same with our confidence interval, which was X bar plus minus Z times the standard deviation divided by the square root of n, which is now turned into X bar plus minus the T times S divided by the square root of n, with degrees of freedom is n minus 1. Very easy, very simple. It is the exact same way, and I'm going to walk you through it on how to look at the table and how to interpret everything. But basically, if you understand Z, you're going to understand T. Let's have an example, once again with IQ. So we have a group, and in our sample we found that there is the mean score in our sample was 110. Our mu is still 110, 100. We found our group, our sample group, had a standard deviation of 10, and our group had 30 participants. Let's first do the significance test. So we start with our hypothesis. So our hypothesis is that mu is 100 versus mu is more than 100. That is our basics. Now let's put it into our formula. So our T formula look like this. Divided by n. So let's plug that in. 110 minus 100 divided by 10 divided by 30. And if we plug that in, you can put it in your calculator, you get 3.734. Now what? Well, we have to look at our degrees of freedom. Degrees of freedom, which is n minus 1. So we look at our n, which is 30, minus 1 is 29. That is our degrees of freedom. Now we're going to look at our table, and we're going to find what we're looking for. So this table used to confuse the hell out of me. So don't feel bad if you feel like intimidated by it. But basically, you over here, you see the degrees of freedom. And you basically just look it up. So we had a degrees of freedom of 29. So it's over here. And now you're just going to look to see if that 3 point something something is in here. As we can see, the highest number is over here, right there. So 0.005, our result was even smaller. So our P is smaller than 0.0005. If we're going to assume the alpha level of 0.05, which is usually the case, this is way smaller. So we're going to reject the null. And that's it. That's literally all you do. You basically, the only difference is that you'd look at a different table. You have to quickly look at your degrees of freedom. And that's the only difference. I found that when I was doing stats, I was majorly confused until I looked at it as in like, oh, these are the same formula with one extra tiny step. Which was very frustrating. But, you know, that's why I'm doing the video now. So we got that one. Now let's do it again with the same sample, like the same things, but now let's do the confidence interval. So our formula is plus minus t times s divided by n. Well then, let's look at our t, because we used to have that z-score and we could just very easily look over here and see that it was 1.96. Well, we can't really do that anymore. So what do we do now? Well, we got that degrees of freedom still, which is n minus 1 is 29. So let's look at 29. And if we want to have a 95% confidence interval, it's over here. We just look at that. There we go, 2.045. So our formula now is 2.045 times 10 divided by 30. That's it. Then we're going to plug that in. So that would be a total of, let's see, 3.734. So we're going to have 110 minus 3.734 and 110 plus 3.734 is 106.266 and 113.734. So our interval is now 0.6.266 and 113.734. That's it. That's the only difference. It is a small extra step, but that's it. And that is all you need to know for the one sample T procedures for both the significance test and for the confidence interval. And now let's do the two sample T procedure, which is once again basically just the Z procedure with a few extra steps. So the Z procedure for the standard, like the significance test, was Z x bar 1 minus x bar 2 divided by the true population standard deviation divided by n plus, there we go. That was the entire formula, and we're gonna change only one small part. So now we have the t procedure. Still just the x bars compared, divided by the square root of standard deviation of the sample squared, n1 plus, there we go. And now, because we have two samples, we have two n's. How do we know what to use for the degrees of freedom? Well, because it's an independent two sample, which there will be a different one that we'll go over where it comes to pooled and that sort of thing, but that's all future stuff. We basically just look at which one of these is the smallest. So the min n minus 1. So if I'll show it in the example in a second, but that is how you find the degrees of freedom for this one. Then when it comes to confidence interval, we used to have x1 minus x2 plus minus z times the square root of standard deviation squared divided by n1 plus standard deviation squared divided by n2. And that is now changed into x1 minus x2 square, like plus minus t times the sample standard deviation 1 divided by n1 plus the sample standard deviation 2 squared divided by n2. That's it. That is the only thing, and we still use that degrees of freedom to find our degrees of freedom. So you look at the minimum sample size. So let's look at an example. Let's say we have, once again, two groups. For x1, we have the basically the sample was, let's see, can't read my own notes, 110, a standard deviation of the group of 15. So that's our sample standard deviation, and an n of 30. And in our second group, we have 115, a sample standard deviation of 10, and an n of 40. Now let's first do the significance test. So first, we have to do our hypotheses. So our null hypothesis is going to be that sample 1 and sample 2 are the same, versus our alternative, that is sample 1 and sample 2 are not the same, that there is a difference between the two of them. Then we plug them in to our formula. So that is 110 minus 115 divided by square root of 15 squared divided by 30 minus 10 squared divided by 40. That is our formula, and out of that we get minus 1.581. How do we get our degrees of freedom? Well, we look at our two sample sizes, and we see that our smallest is 30. So our degrees of freedom is the smallest sample size, so that's 30, minus 1 is 29. Then we look at our D table, look at 29, then we try to find where our group is. Well, it would fall in between these two. So our P would be between 0.1 and 0.05. If we assume our alpha level of 0.05, which usually it is, we see that our P is bigger than our alpha. Therefore, we fail to reject the null. So we accept the null to be that the difference between the two is similar enough that we just accept the null hypothesis. And that's it. So now let's look at the confidence interval. So for this one, we have x1 minus x2 plus minus t times s21 n1 plus s22 divided by n2. Let's calculate that. So that is 110 minus 115 plus minus. How do we get that t? Well, we'll once again look at our degrees of freedom, which would be the minimum, so 30 minus 1. We look at it. If we want to have a 95% confidence interval, we would look over here, and we see that it's 2.045. So it's 2.045 times the standard deviation 1 squared divided by 30 plus standard deviation squared divided by 40, and you get 6.47. So now it's 110 minus 1 minus, and 110, 115 plus 6.747 is minus 11.47 and 1.47. So our interval would be minus 11.47 and 1.47. We see that 0 falls in between this interval, which would also correlate with our significance test, that we see that it's not significant because we can say with 95% confidence that the 0 falls in between this interval. So there is just a chance that there is no difference between the two. And that's it. It's a lot easier than my massive behemoth of a part 1. But that is everything you need to know about T procedures for both the 1 sample and the 2 sample.